Welcome back to today's session. In the previous session, we learned how to use graphical method for maximization problem. Today we will be looking at how the method can be used for minimization LPP. So to understand the procedure of solving LPP minimization type using graphical method, let us consider a problem and solve it. So almost the procedure of solving minimization problem is very much similar to that of maximization problem. So the problem that I consider is minimize z is equal to 20x1 plus 10x2 subject to x1 plus x2 less than equal to 40, 3x1 plus 3x2 greater than equal to 30, 4x1 plus 3x2 greater than equal to 60, x1 comma x2 greater than equal to 0. See, one thing I would like to tell is, see, there is no compulsion that if you have two decision variables, I need to have only two constraints. So minimum of two constraints are necessary. More than two, you can have any number of constraints. The more number of constraints you have, the more accurate or more optimal solution you would get. So now we'll consider this problem and try to solve it. So minimization case, z equals 20x1 plus 10x2 subject to the constraints. So as usual, like in maximization, in minimization also I'll have to consider the constraints as equation and generate the coordinate points. So I'll consider the first constraint as an equation. So the first constraint was x1 plus 2x2 less than equal to 40. So that will become x1 plus 2x2 is equal to 40. So I'll put x1 is equal to 0. So 2x2 becomes 40. Therefore, x2 will be 20. So the coordinate point that I get is 0, 20. Now I put x2 is equal to 0. So I get x1 is equal to 40. So the point that I get is 40, 0. Now consider the second constraint. The second constraint was 3x1 plus x2 greater than equal to 30. So when I consider it as an equation, it becomes 3x1 plus x2 is equal to 30. So I put x1 is equal to 0 there. So it makes x2 is equal to 30. So the point that I get is 0, 30. Now I put x2 is equal to 0. That makes the equation 3x1 plus 0 is equal to 30, which makes 3x1 is equal to 30, which implies x1 is equal to 10. So the point that I get is 10, 0. Now considering the third constraint as equation, the third constraint was 4x1 plus 3x2 is greater than equal to 60. So when I consider it as an equation, it becomes 4x1 plus 3x2 is equal to 60. So when I put x1 is equal to 0, so I get the equation as 3x2 is equal to 60. Therefore, x2 is equal to 20. So the point will be 0, 20. Now put x2 is equal to 0. So I get 4x1 is equal to 60. So x1 is equal to 15. So the point that I get is 15, 0. So the coordinates that I've got 0, 20 and 40, 0 for first equation, 0, 30 and 10, 0 for the second equation, 0, 20 and 15, 0 for the third constraint. Okay. Now we'll see. So coming to the plotting, as usual, I consider x-axis and y-axis. See, in my case, I wanted up to 40. Therefore, I consider y-axis as x1, x-axis as x2. Fine. So I am considering the scale as 2. So 0, 2, 4, 6, 8, 10, 12, 14, so on up to 40 along x1, 0, 2, 4, 6, 8, 10, so on up to 30 along x2. So this will be your first quadrant area where you will get the solution. So the first equation coordinates was 0, 20 and 40, 0. 0 along x1 and 20 along x2. So this will be the point. Then 40 along x1 and 0 along x2. This will be the point. So when I get two coordinate points, 40, 0 here and 0, 20 here, I join it with a straight line. And the constraint was less than equal to type. So because it is less than equal to, below the line or to the left side of the line, I am supposed to shade. So to the left side of the line or below region, I am shading it. Fine. Now consider the second equation. The second equation coordinates are 0, 30, 0, 30 and 10, 0. Right? So I have got two coordinates, 10, 0 here and 0, 30 here. Now I join them with a straight line, and here the constraint is greater than equal to type. So I am supposed to shade the above region or the right side of the line. The above region of the line is shaded. Now consider the third constraint. So the third constraint, before going to the third constraint, see here, this region above the line, above this line, so this portion is also accepted. This portion also satisfies the constraint of the second equation. Fine. This entire region is supported. Now consider the third equation. The coordinates point was 0, 20, this point, and 15, 0, this point. So I join these 2 points with a straight line, and the constraint was greater than equal to type. Therefore, above the line or to the right side of the line, shading has to be done. So above the line, I am doing the shading. Blue shade is for this particular line. So anything above the line is a feasible region. So for the first equation, green shade below the line. For the second equation, pink shade above the line. For the third equation, blue shade above the line. So now the region where I have got all the 3 shadings is the feasible region. So if you have a look, this particular region, this quadrilateral has all the 3 shadings in it. So I will highlight it with a different color. So with orange, I have just highlighted this region, and I am supposed to mark the extreme points. The extreme points A is 15, 0. Extreme point B is 40, 0. Extreme point C is almost, it must be 5.8 and 18. No, not even 18. It is 17.8. So 5.8 and 17.8, and D is almost 6 and 12.2. 6 and 12.2. So these coordinates we are supposed to substitute in the final table, Z table. So the points are A at 15, 0, B at 40, 0, C at 4, 17.8, D at 5.8 and 12.2. Fine. The objective function was z equals 20x1 plus 10x2. So when I substitute these coordinates in the objective function, it becomes 20 into 15 plus 10 into 0, which will be 300 plus 0. So 300 plus 0 is 300. I write it in the value column. Now B is 40, 0. So when I substitute it in the objective function, 20 into 40 plus 10 into 0. So I get a 800 plus 0. So the value written in the value column is 800. Now C is 4, 17.8. So when you substitute it in the objective function, you get 20 into 4 plus 10 into 17.8. 20 into 4 is 80. 17.8 into 10 is 178. 80 plus 178 gives you 258. Now coming to point D, which is at the coordinate 5.8 and 12.2. So 20 into 5.8 plus 10 into 12.2. 20 into 5.8 is 116. 10 into 12.2 is 122. 116 plus 122 is 238. Now the difference between maximization and minimization is observed now. There I was highlighting the one with the highest value, but here it is minimization case. The one with the minimum most value 238 is highlighted. So that will be your Z min value. Z min is equal to 238 at x1 is equal to 5.8 and x2 is equal to 12.2. Any doubts with this method? It is very much similar to maximization case. The only difference is while highlighting the value in the Z table. There I am highlighting the row with the highest value. Here I am highlighting the row with the least value or the minimum value. Hope you have understood. Shall we move on? Right. Now a problem for you to try it out. So the problem is minimize z is equal to x1 plus x2 subject to 5x1 plus 10x2 less than equal to 50, x1 plus x2 greater than equal to 1 and x2 less than equal to 4. So when you have a constraint x2 less than equal to 4, it is nothing but 0 plus x2 is equal to or less than equal to 4. So you will get a straight line here, which will be, I think, a vertical, not vertical, because I am considering x2, you will get a horizontal line for this constraint. Fine. Try it out. Whatever answer you get, post it in the comment section of this post. If at all you have any doubts, that also can be posted in the comment section. I expect every one of you to try out the problem, solve it, and give me the answer. Shall we move on? So for LPP, when I consider graphical solution, I have different types of solutions that I can get. The LPP can have different types of solutions like unique optimal solution. Till now, the two problems that we saw had a single point at which either the maximum or the minimum value was obtained. Therefore, I call it unique optimal solution. Optimal solution is available only at one point. Therefore, it is called unique optimal solution. Multiple optimal solution. How does this look like? So I'll just come back to the previous example here. Let me say I had a point D at some coordinate and I had a point C at some coordinate, and when you substitute it and you get the values let me say I got a 238 here also and a 238 here also. Both are optimal solutions, both are correct, both are optimal, but it is not unique. A single solution or a single point is not giving us a solution. Multiple points might lead to the optimal solution. Under such situations, we call that scenario as multiple optimal solution. One more type of solution that we get is unbounded solution. I am trying to find out the maximum value and I don't have a closed figure. So the maximum can go up to infinity. It can go up to infinity. Then I call it unbounded solution. We will see it with an example in the next slide. Then no solution. Let me say I try to plot the lines. The lines do not intersect at all. It does not give a feasible region only. In such case, there is no question of me getting an optimal solution because feasible solution only is not getting generated. Only if at all I get a feasible region, that is the orange region, then I can find out extreme points and I can find out that as the optimal solution. But here I am not getting that orange region only. That feasible region only is not available. That situation will be arised because the system of constraints that I have is inconsistent. This no solution type is also called system of inconsistent constraints. So that also we will have a look with an example. So now coming to unbounded solution example. So I consider an example for unbounded solution. In this, the problem is maximization. Most of the unbounded solution problems will be maximization type because minimization type having an open figure in the first quadrant below at the lower end is quite rare. Therefore, unbounded solution for minimization problems are quite rare. Therefore, we encounter maximization unbounded solution most of the times in maximization type problem. So one example that I consider, max z is equal to 3x1 plus 2x2 subject to the constraints x1 minus x2 is less than equal to 1, x1 plus x2 greater than equal to 3, and the non-negativity constraint x1 comma x2 greater than equal to 0. So when I try to solve this problem, so as usual, first constraint as equation x1 minus x2 is equal to 1. So when I put x1 is equal to 0, I get minus x2 is equal to 1, which makes x2 is equal to minus 1. So the point that I get is 0 comma minus 1. Put x2 is equal to 0, I get x1 is equal to 1. So the point that I get is 1 comma 0. So the coordinates for the first equation is 0 comma minus 1, 1 comma 0. Consider the second constraint as equation x1 plus x2 is equal to 3. Put x1 is equal to 0, I get x2 is equal to 3. Put x2 is equal to 0, I get x1 is equal to 3. So the points are 0 comma 3 and 3 comma 0. Fine. So once we have computed these coordinate values, we'll try to substitute it. So considering the first equation, I get the point to be 0 comma minus 1, 0 along x1 and minus 1 along x2. So this is the point. So the point is outside the first quadrant, right? But still not a problem because the line can be extended on either sides. So here the point is 0 comma minus 1. Other point is 1 comma 0. 1 along x1, 0 along x2. So this is the point. So the line that I get is from here to here. Fine? From here to here. But I am supposed to extend it on either side so that it passes through the first quadrant. And it is less than equal to type constraint. So to the left of the line, I am performing the shading. So this entire region is to be shaded for the first equation. Now consider the second equation. Second equation points was 0, 3 and 3, 0. 0, 3 is this point, 0 along x1, 3 along x2. Now 3, 0, 3 along x1, 0 along x2. This is the point. So I draw a line here and extend it if needed. And this is greater than equal to type. So to the right of the line or above the line, I am supposed to shade. So this entire region is feasible for second constraint. Now the region which has both the shadings, I have highlighted with orange. So the extreme points, I can find A here, B here, but it is not a closed figure. This region, this particular region gets extended up to infinity in this place. It can keep going on. It is not bounded with a line. It is not covered with a line. So because I am not getting a closed figure, the maximum value can go up to infinity. Therefore, we call it unbounded solution problem. So here you will not get a maximum value because maximum can go up to infinity because the top portion is not sealed. It is not covered by a line. Therefore, it is unbounded. Clear? Any doubt with this? So whenever I have a maximization case problem and the top portion is not sealed, it is not covered, it can go up to plus infinity. Therefore, we call it unbounded solution problem. Now we will have an example for no solution. Right? No solution or inconsistent system of inconsistent constraints. So the problem that I consider is max z is equal to 3x1 minus 2x2 subject to x1 plus x2 less than equal to 1, 2x1 plus 2x2 greater than equal to 4, and non-negativity constraint x1, x2 greater than equal to 0. So when I try to solve it with the procedure, first constraint as equation x1 plus x2 is equal to 1, x1 is equal to 0, x2 is equal to 1. When I put x2 is equal to 0, I get x1 is equal to 1. So the points that I get is 0, 1 and 1, 0. Now consider the second constraint, 2x1 plus 2x2 is equal to 4. So when I put x1 is equal to 0, I get 2x2 is equal to 4, which makes x2 is equal to 2. When I put x2 is equal to 0, it makes 2x1 is equal to 4, which makes x1 is equal to 2. So the points that I get is 0, 2 and 2, 0. When I try to plot it, how does it look like? So the first point is 0, 1, 0 along x1 and 1 along x2. So this is the point. Right? Next, 1, 0, 1 along x1, 0 along x2. So this is the point. So I get a line here. I extend it on either side and I am supposed to shade the region. This is less than equal to type constraint. So I am supposed to shade below the line or to the left of the line. So the region in the first quadrant which is below the line is only this much. Right? This is the feasible region for the first constraint. Now consider the second constraint. So the second constraint points that I get is 0, 2 and 2, 0. 0, 2 is this point. 2, 0 is this point. And it is greater than equal to type constraint to the right of the line or above the line. The region above the line, this portion, this entire portion is a feasible region for second constraint. The feasible region for first constraint is this. the region for the second constraint is this, and we observe that it is not intersecting only. If it is not intersecting, there is no common feasible region. If there is no common feasible region, how do we find optimal solution out of it? So obviously question of optimal solution does not arise at all. So this type of situation is called no solution or system of inconsistent constraints. Hope you have understood graphical method. This is the end of graphical method. In the next session, what we would be doing, we shall discuss in our Zoom session. Till then, thank you. Have a nice time. Enjoy. Be home. Be safe. Thank you.